Lab 4, Rope Physics. In this lab, we examine the motion of a spring that is oscillating in the x and y directions. The motion of the spring is used to model the motion in extreme rope sports. From the tracker file, I analyzed the motion of the spring and used Python to model the motion. In this lab, the fundamental principles that are necessary are the energy principle and Newton's second law of motion. We use Newton's second law of motion in order to predict the spring's new velocity and its new position. The form of Newton's second law that we use is the final velocity is equal to the initial velocity plus the F net over the mass times delta t. The second fundamental principle is the energy principle. The energy principle is the total energy of the system is equal to the kinetic energy plus the gravitational potential energy plus the spring potential energy. Now for my code. In this part of the code, I identified all of the initial conditions such as the mass of the ball, which is 0.042 kilograms, the position of the ball, which I got from the tracker file, and then here I read in all the position values that I had extracted from my tracker file. These lines of code are where I initialize the other variables that are necessary for the calculations. G is the gravitational constant. Here, the spring constant and the relaxed length of the spring are calculated using these equations here. T is the period of oscillation, which was calculated from the graph from the tracker file, and the initial length of the spring was 0.7 meters, which was given. From these values, I was able to calculate the spring constant and the relaxed length of the spring, and it was just a matter of manipulating the equations. Here, these lines of code calculate the length of the spring at each time interval. L hat has the spring's direction, and S describes the stretch or compression of the spring, which is used to compute the spring force and the spring energy. Now for the system's energies. The energies that are present in the system are the kinetic energy, the gravitational potential energy, and the spring potential energy. The kinetic energy was calculated using the equation 1/2 mv squared. The gravitational potential energy was calculated using the formula mgh. And the spring potential energy was calculated using the formula 1/2 k, which is the spring's constant, times s squared, and s is the spring stretch or compression. Alright, here I calculate the initial energies and set them equal to these variables, which I used later on. The values of these variables will change as the system moves. Now here is where I calculated the net force of the system. Since the net force is composed of the gravitational force and the spring force, I calculated both of these now. So here's the gravitational force. For this, I used the equation negative mg, and since it's in the y direction, it's set in the y component of the vector. Now for the spring force, I used the equation negative ks times L hat. For F net, I took the sum of the gravitational force and the spring force, and then I used that F net in Newton's second law to predict the new velocity of the spring system. Here, I predicted the new position of the spring system at each new time interval. Then the spring is updated. The position of the spring changes, and so does the stretch and the compression. These lines here make the spring move and updates the visual aspect. The last thing I edited is the new energy of the system at each time interval. The kinetic energy, the gravitational potential energy, and the spring potential energy change and have to be recalculated and updated. Changes in each of these energies are then stored and plotted so that we can see the energy change at each time interval. Now for my Python code. Here I graphed the position of the spring simulated using Python and the values taken from Tracker so we can compare them. Based on the graph and the motion of the red and the blue balls, the Python code simulates the motion properly with only a slight error. As we can see here from the graph, the actual motion of the spring varies slightly compared to the motion that is calculated by the Python code. With this code here, I graphed the energy changes of the system. The blue line is the kinetic energy, the red line is the spring potential energy, the green line is the gravitational potential energy, and the yellow line represents the energy change of the system, and the energy change of the system is 0. Since the spring has motion in the x and the y direction, it has a period of oscillation for the x and the y. Components. The period of oscillation for the x direction is 1.679 seconds, while in the y direction the period is 1.52 seconds. These two values are different because the period of oscillation for the x direction is based upon different values than the period of oscillation in the y direction. For the x direction, the period is found using the formula T equals 2 pi times the square root of L over G, where L is the spring's length and G is the gravitational constant. In the y direction, the period is found using the formula 2 pi times the square root of m over k, where m is the mass and k is the spring's constant.